Hello, good morning. Let's begin. We are going to try to finish lecture 9 today, but there are a lot of things to cover. So, depends if you guys have more questions or not, we might or might not finish, but we'll try. We'll try to finish it. So last class, we learned all about the structures of the kidney. We know, the different parts that it's made up of. We learned about the functional unit of the kidney, which are the nephrons. And so today we're gonna begin by talking about the formation of urine. Formation of urine. Okay. So the urine formation process depends on three functions. And these are all happening in the nephron. The first function is called filtration. Filtration. And these are in the PowerPoints as well, but like I'm just gonna give you like a condensed version of it. Filtration is basically the process that involves the movement of fluid from blood into the Bowman's capsule. The Bowman's capsule. Yeah, so we'll talk more about that later, but that's the initial step. Right? I'd like to think of urine formation as similar to like cleaning out your closet. Yeah, I don't know if this is something that people have shared experience of, but when I try to clean out my closet, it's like it's springtime now, so we could put away the winter stuff. Right? So to clean out the closet, I usually take out a bunch of clothes and then just dump it on the floor. Okay, that's my initial step. So that's kind of like the filtration process. You just take a bunch of stuff from the blood and then you put it into the Bowman's capsule. Now, all this stuff that I took out, I'm probably gonna keep, most of it. I need to put it back in the closet. But it's just easier if I dump it all out first and then I sort through the clothing one by one, right? So similarly, when you take all this stuff out from the blood initially, there are not like good stuff in it. Right? There's some nutrients in it that you want to take back. But it's just easier to, let them all go out into the Bowman's capsule first. Which is why the second function is reabsorption. Reabsorption. And reabsorption is the transfer of essential solute and water from nephron back into blood. Right? So, as I sort through the pile of clothing that I just dumped out, I'm like, okay, I'm gonna keep this, I'm gonna keep this, and I take all the things that I want to keep and put it back into the closet being the blood. Okay. So you're gonna reabsorb essential solute like here, I'll put it here, e.g. like sodium. You might take back some glucose, like useful stuff. And then finally, there's also secretion. Secretion. So in secretion, this involves the movement of material from blood back into nephron. So as I put some of the clothing nicely back into the shelf, I might notice, oh, hey, there is that, sweater that, I no longer fit or something. And there's like these things that, oh, I no longer need. And I actually want to get rid of it. So like I would take them out and then put it back in the pile again. So as the blood as the fluid continues, as the we call it the filtrate, right? Continues in the nephron. Later on, you might find out you still have some waste product in the blood that you've missed initially in the filtration process. Okay, and that you want to put it back into the urine. And so there's this like fine adjustment happening as the filtrate gets passed through the nephron. And so that's called like reabsorption and secretion. So basically, it goes something like this. Okay, you're gonna have your nephron right here. This is your nephron. Okay. And I hope you remember the parts. This is the Bowman's capsule, proximal tubule, loop of Henle, distal tubule, and what's this last part called? Anybody remember?
The canal, something like that.
It starts with a C, yeah, but not the canal. Good try though. Anybody? Can you take a look at what we wrote down last time? You know, maybe it's a good idea to spell them all out. Bowman's capsule. That's right, Sarah, the collecting duct, yes. Collecting duct. Right. DT is distal. Distal tubule. Proximal tubule. And then the loop of Henle, right? So what happens is we have the afferent arteriole coming in. We're gonna have the glomerulus. Right. Now, don't forget, this blood vessel actually will form a web. Okay, but like for simplicity's sake, I'm just gonna draw it as like a blood vessel that's like right next to it. But you know it's gonna open up as a web, right? We talked about this last time. Okay, so this is the peritubular capillary. Right. Just gonna label all of it for you. What's that thing called right here? That little network of blood vessel? Anybody? What is that thing?
The glomerulus capillary.
Yep, you got it. That's the glomerulus. Very good. Okay. Now, this is what happens, okay? We're gonna have the filtration happening at the beginning. Filtration. I'm just gonna use the blue arrow. And that's like the stuff coming out. Blue arrow. Filtration. That only happens in the glomerulus. I'll tell you more about it, okay? That only happens in the glomerulus. And then, as we go on, we're gonna have two things happening at the same time, right? We're gonna have reabsorption and secretion. So reabsorption is going from blood, it's going from filtrate back to blood. So you're gonna have reabsorption happening in the proximal tubule. You're gonna have reabsorption happening in the loop of Henle on the way down and on the way up. You're also gonna have reabsorption at the distal tubule as well as the collecting duct. Okay, so green arrow is reabsorption. Reabsorption. You're taking stuff back into the blood. These are things that you want to keep, but you know, it just happens to be lost. You know, accidentally, I suppose. Well, not accidentally. It's more like, it's like it was by design, right? Like in the filtration process, it's not very selective, so you end up losing some of the useful stuff. And then you're gonna have secretion. This is like stuff that you missed, you actually want to get rid of, but you missed it in the filtration step. So that's gonna happening in the proximal tubule. And notice the direction of the arrow, it goes from the blood to the filtrate, right? So that happens in the proximal tubule. It does not happen in the loop of Henle, and then it happens again in the distal tubule. Okay, and a little bit in the collecting duct as well. Okay, sometimes. All right. I'm just gonna take a pause here and see if anybody want to ask anything. So that's like the overview of what's happening with the urine formation process. Okay. All right. So let's talk about. Let's go back to PowerPoint slides. And this is basically what I wrote down for you, but in like a more condensed way. So let's look at what happens in the filtration process. Filtration is the first step, and it only happens in the glomerulus, in the Bowman's capsule. Right? And last time at the very end, I told you, like, there's this term renal corpuscle. That is just the Bowman's capsule plus the glomerulus. Right? So fluid's going to be coming out from the glomerulus, and everything's going to be captured by the Bowman's capsule. So as you know by now, the each nephron of the kidney has an independent blood supply. Right? The afferent arteriole is going to be feeding into each of the nephron. And the blood moves through the afferent arteriole into the glomerulus. And the glomerulus, I told you, is basically capillary, but it's like extra leaky. And the pressure inside the glomerulus is actually much higher than normal capillaries. Okay, so the blood pressure in the glomerulus is about 60 to 90 millimeter mercury, and your body can adjust for the pressure by changing the diameter of the afferent and efferent arteriole. Just for reference, normal capillary is about 25 mmHg. Okay, 25 mmHg. You might remember this number, right? We talked about capillary exchange a long time ago. Right? On the arterial end, blood pressure is about 30. On the venous end, it's about 15. So in between, it's about 25 mmHg. So in the glomerulus, it's like, a little bit over 2 times and sometimes 3 times as high as normal blood pressure in the capillaries. And that pressure combined with the fact that the glomerulus is leaky, it's going to be able to push out a lot of fluids. So along with the fluids, we have dissolved solute, and all these things are going to be coming out, and they are going to be captured by the Bowman's capsule. Things that are large, like proteins, blood cells, that includes all the cells, okay? Red cells, white cells, platelets, they don't pass through the walls of the glomerulus. They stay within the blood. And anything that's not filtered is going to continue on into the efferent arteriole. Okay, so on average, we have about 600 milliliters of fluid, okay, passing through the kidney. Passing through kidney per minute. And approximately 20%, okay, 20% of 600 is about 120 milliliters. About 20% of this fluid is filtered into the nephron at this first step, at the filtration step. Okay. So, I mean, like, if we don't take it back, then that means every minute we are going to be producing 120 milliliters of fluid, which means we're going to be peeing out, all the time. And in order to survive, we would have to basically continuously drink fluid. We have to drink as much as like 1 liter of fluid every 10 minutes just to maintain homeostasis. But fortunately, of the 120 milliliters of fluid that's being filtered out into the nephron, we actually will take back most of it. Okay. Of the 120 milliliters, we only pee out 1 milliliter of urine. Okay. So for every 120 that we filter out in the filtration process, we're gonna take back 190 milliliters. Do you understand what I mean? Hey, maybe I put it out in like some numbers for you. Okay. So like 600 milliliters, it's gonna go into the glomerulus, basically. Like all of the glomerulus collectively, right? Not individually, right? Like millions of them. And then what happens is, you will have 120 that is filtered. Filter. Okay. And this is going to become the filtrate. Filter into nephron. Okay. So this is afferent arterial. So that means 480 milliliters will continue out into the efferent arterial. I mean, you don't really have to understand these numbers too much, okay? But like, I just want to see if you with some numbers, maybe it's better for some of you. Okay, so 600 goes in to all the nephron, and then you filter out 120. The other 480 will just continue in the efferent arterial and then becomes part of the peritubular capillaries. And then as time goes on, as the filtrate passes through the rest of the nephron in the proximal tubular loop of Henle distal tubule, you will take back 119 milliliters. Okay, and then you will just end up having 1 milliliter of urine. Okay, which makes sense. Otherwise, we're gonna like dehydrate super quickly, right? So this process is reabsorption. Is that okay? And then this just like basically goes back to circulation, right? And this happens continuously. Right? Continuously. Questions? Okay. So what is in the filtrate that comes out from the glomerulus? The filtrate is described as a protein-free plasma. You remember plasma? If you spin down blood, you will get the cell at the bottom, and the fluid portion at the top is called plasma. It's mostly water. It has dissolved molecules in it, right? Minerals, nutrients, waste product, and proteins. So if you remove all the proteins from the plasma, that's basically what the filtrate is. Okay, proteins are too big to leave. Okay? So cells and proteins, they are the non-filtered component, and they will continue on to the efferent material. Whereas all these things, the water, the waste, right, glucose, nutrients, salt, right, all of them are going to come out and be captured by the Bowman's capsule. Now, again, I have to emphasize, at this point, it's not that all the waste product are going to come out. You're only filtering 20% of what's coming in, right? Like some of it you're going to miss, which is fine. Later on in the nephron, you might put more in, but then since you continuously filter the blood, right? Some of the material that you've missed this round, you will have to wait for the next round of filtering. Right? Like when the blood circulate once and then it comes back to the kidney again, then you can filter it. That's why it's like a continuous process, right? It's not like you can remove all of it like right away. If you look at a fish tank, that's basically the same kind of filtering system, right? You got to keep on circulating the water. You catch as much as you can, and then as more water goes through it, you catch more waste product, and you continuously filter the blood. Okay. So that's it. That's it for the Bowman's capsule filtration. Okay, so now we lost a bunch. Sorry, go ahead. Yeah.
Excuse me, like a filtering water in the pool, yeah?
Yeah, exactly. It's like filtering water in a swimming pool. Right? It's like any filtering system. Right? The filter is not going to be 100% filtering out everything the first go, right? It needs to be a continuous process. So now we're going to move on to the proximal tubule. And like I said, it's important we absorb back, especially the water, right? Along with some nutrients from the filtrate. The filtrate is the stuff in the nephron, okay? And the filtrate is what will become the urine eventually. Okay, so the filtrate is inside nephron, and it becomes the urine eventually. And right now it's not like the final thing yet. Right now it's still nutrient rich, lots of water in it. Okay, so we're gonna take back a lot of the stuff in the proximal tubule. Okay? In fact, at the proximal tubule, approximately like 60 to 70% of the filtrate are gonna be reabsorbed here. Okay, so approximate. Do I have a slide coming up? Yeah, about 60 to 70% of the volume of the filtrate that were produced from the Bowman's capsule will now be reabsorbed in the proximal tubule. So what are we taking back? Like I said, water, glucose, amino acid, sodium chloride. And to bring them back, we have to use both active and passive transport. Of course, you remember these, right? Active transport requires energy, whereas passive transport does not. Now, what's important is that every substance requires a carrier to transport them. And when all the carriers are working at maximum speed, a threshold level of that substance is reached. Let me try to explain this to you. Okay. I guess the best way to think about this is like this. Okay. You have a conveyor belt here, and then there are like I don't know, potatoes or something. Okay, potatoes, and then every now and then there are some I don't know, bad potatoes or something. It doesn't. Sorry, it doesn't have to be potato. It could be something. Okay, whatever you want this to be. But there are some like orange one, and then there are some like black ones. Okay, and then you have another conveyor belt here, another conveyor belt here. So imagine you have a bunch of workers here, okay? A bunch of workers, and the job of these workers is to take all the orange ones and then put it onto the other conveyor belt. Okay, can you guys understand my analogy here? Okay, two conveyor belt, we have a bunch of people who have their job is to pick out the orange ones and then put it here. I guess think of them as eggs. Maybe eggs are better because some eggs are white, some eggs are brown. Okay, so the job is to take all the brown eggs and then put it onto the other conveyor belt. Now here's the situation. Okay, if everybody is working as fast as they can, and remember these are conveyor belts, right? So the belt keeps on moving regardless. So if everybody's working as fast as they can already, then there is a chance. I mean, it's not a chance. There is going to be some eggs that are going to be missed if there are too many like brown ones, right? If everybody's working at full speed already, you're going to miss some of these brown eggs, and then it will just continue on the black conveyor belt, right? What am I talking about? How is this relevant to the whole kidney situation? Well, this is the proximal tubule. And just make me feel better, guys, that I know you know what I'm talking about. What is this red thing here? If this is proximal tubule, what is this red line? Look at your notes. Tell me, please.
Distal?
Well, the distal tubule would be later on after the loop, right? And then the distal tubule. But this is something that's parallel to the proximal tubule. It's always there.
The peritubular capillary.
That's right, the peritubular capillary, right? That's the blood, by the way. That's where the blood is. And what do we call the stuff inside the proximal tubule? What do we call the stuff that's inside the proximal tubule? That's okay. It's the filtrate. The filtrate. Okay, so filtrate has mostly water, and then it has nutrients like glucose. Okay, so I'm going to use these green dots. Okay, glucose, and there are a bunch of other stuff as well. Okay, whatever they are, doesn't really matter at this point. Okay, so let's say these are glucose. So how do I take the glucose back into the blood? Then you would need to have these glucose transporters. Okay, these are transporters, protein transporter. And so it will take the glucose and then it will move them over, it'll move them over, it'll move them over. So normally they do a good job absorbing all the glucose. Right? However, in a situation where the person has like way too much glucose in their blood, such as like type 1 diabetes, not having insulin at the moment, okay, there will be too much. And if all the transporter is working at full speed, then you are not going to be able to absorb all the glucose, right? And so the remaining glucose is going to continue on into the loop of Henle and then into the distal tubule, and eventually it's going to come out in the pee. Okay, so two things to take away from here. Number one, to absorb the molecule, I need to have a transporter. Okay, let's say there is like these purple ones. To absorb the purple ones, I need to have a purple transporter. Okay, that's the number one thing to take away. Number two is if the transporter are working at full speed, you won't be able to absorb that thing further. So that's why every substance is going to have a threshold level. Okay, threshold level refers to the maximum amount that you can take back. If your filtrate level, if the level of the substance in the filtrate is higher than the threshold, you can't take them back any further. You're just gonna pee them out. Okay. Now, thirdly, because you need to have a transporter to take the things back, right? Sometimes we might eat things, we might consume things from the food or from drinks that contains substance that we do not have a transporter for. Okay, and if we don't have a transporter for it, then we won't be able to take them back to the blood. It will stay in the filtrate. An example of that is caffeine. If you drink coffee, all the caffeine is just going to stay in the filtrate, and then you're just going to pee it out. And so there are two implications of that, which we'll get to later. But like, that's why people say if you drink coffee, the pee smells like coffee. That's the caffeine in the urine. Your body doesn't reabsorb it. Okay.
Sir, what about alcohol, like beer?
Yeah, okay. So alcohol is very different because alcohol is water soluble, right? So it just stays in the water, and you might reabsorb a little bit of it, but for the most part, it's just gonna come out as well. Okay, but the alcohol does stay in the body for quite some time, because during the urine filtration process, you actually would be able to take some of it back into the blood, right? So that's why it stays there much longer. There's like this new commercial that I hear on the on the radio these days. They're saying it it goes something like this, like, oh, you went out to party last night and then you did the right thing, you had a designated driver, and then they say, did you know if you drank a lot, the next morning you wake up, your blood alcohol level might still be too high. And they're like, hot shower, full meal and coffee, those don't actually clear the blood. The only thing that will clear the alcohol from the blood is time, they say, right? So it takes time for the body to basically filter it up. And a lot of the alcohol has to be broken down in the liver first, right? Before you are able to pee out the metabolites, right? Okay. So like we don't actually pee out like alcohol as is. Your body has to break down the ethanol first. Anyway, that's that. Any other question? Okay, so what do we absorb? Mostly water, nutrients, salt. We actually inadvertently take back some waste product as well. Okay, and then these are things that are not taken back. Yeah, you take back most of the water, but you cannot take back all the water. If you take back all the water, it's completely dry. Nothing's gonna flush the nephron, right? Okay, and these things we don't take back. Okay, molecules not recognized by carrier, like drugs. Okay, like we not necessarily like illegal drugs, like medication or medicine. Medicine, we don't. It's not a naturally occurring thing in the body. We don't absorb it back. Okay, so 60 to 70% of the volume of the filtrate produced here are going to be reabsorbed. So again, right, think of the numbers if it helps. If you're a number person, right? So 120 came out, we're taking back about 70%, right? So what is 70% of 120? About 84 milliliters. Okay, taken back collectively, right? Of all the nephrons working together. All right. Absorption of each ion is tightly regulated by the amount present in the blood as well as hormonal control. You don't just take back all the ions randomly. If you already have a lot of calcium in the body, then you're gonna not absorb as much back, right? If you already have a lot of potassium, same thing. You don't want to take too much back. So this is tightly regulated. And one of the functions of the kidney in terms of maintaining homeostasis is to control the pH of the blood. And that was in the second slide, I believe. And part of the regulation happens here in the proximal tubule. Okay, so blood pH is controlled by the secretion of hydrogen ions and reabsorption of bicarbonate ion. And to understand this, I need to give you a quick note on buffers. Okay, buffers. Does anybody know what a buffer is? What is a buffer? Okay, so a buffer, I thought you guys might have learned about this in chemistry, no? Not there yet? Did you guys learn about acid and base in chemistry?
The next acid base unit is next week.
It's next. Okay, so you get to learn it from me first before you learn it from Michu. So buffer is basically like a system, if you would. Yeah, weak acid, exactly. Okay. But you know, you can think of it as a chemical system, a chemical equation, right? Chemical system that resist small changes in pH. Okay? And you know, just so we are clear, when pH is less than 7, it's acidic. Okay? So like lemon, vinegar, those are acidic stuff. When pH is greater than 7, it's basic. So ammonia, bleach, right? Soap, these are basic stuff. Right? And pure water is 7, right? Which is neutral. So when when our body performs cellular respiration, the products are water and carbon dioxide, right? So the carbon dioxide actually reacts with the water in the blood to produce H2CO3. Right? So this here is a carbonic acid, or carbonic acid, some people pronounce it. So carbonic acid is going to actually dissociate. And like NaCl can dissociate, right? It's going to dissociate into H plus and HCO3. Right? And unlike what you might have learned so far, chemical reactions can actually go forward and backwards. Right? Some reactions will only go forward, true, but many can go backward as well. Right? It just shifts back and forth. So this here is hydrogen ion, and here is bicarbonate ion. Hydrogen ion, the more you have, more H plus, I guess higher H plus concentration equals to lower pH, which means more acidic. On the other hand, low concentration of H plus means higher pH, which means more basic. Now, a long time ago, I told you this, actually I told you this last semester. The blood pH, what's the normal blood pH? Anybody? 7 point what? I guess that's not a fair question. It's a really long time ago. 7.35, okay? So that's the normal blood pH. Slightly basic, okay? But, you know, close to neutral. So in the blood, you have this buffer system. H2CO3 is going to break down into H plus and HCO3. The HCO3 is not going to contribute to pH directly. It's the H plus that contributes to pH. So let's say there is, you know, maybe you eat something, you drink a lot of citrusy stuff, okay? Orange juice, red wine, what have you. Then you all of a sudden have a low blood pH. Low blood pH. We'll say drop in blood pH. Drop in blood pH. So what does that mean? If your blood pH drop, is there too much H plus in the blood or not enough H plus in the blood? You need to think about this. Drop in blood pH. Too much or not enough H plus?
Too much?
Too much, right? So we have excess H plus. Excess H plus. So what is your body going to do if you have too much H plus? Well, one way is the extra H plus combines with HCO3 to form H2CO3. So essentially, the HCO3 is a mop to mop up the extra H plus. And then it will put it in the form of H2CO3. And that clears the excess H plus and it brings the blood pH back to normal. Okay? This mops up extra H plus. Now, let's take a look at the kidney here. What does it say? At the proximal tubule, blood pH is controlled by secretion of H plus. So let's say you have excess H plus, right? Which is what we're talking about here. Drop in blood pH, excess H plus. We mop up as much as we can using the buffer. But what if there is still more, right? Well, at the proximal tubule, we can secrete them. Okay, you can take the H plus from the blood and then pee it out. Right? Put it into the nephron, and then you will pee it out. Now, as you are mopping up the H plus using the bicarbonate, you are using up the bicarbonate, right? So we want to replenish the bicarbonate. So how do we get more bicarbonate? Well, you at the proximal tubule, you are going to promote reabsorption of bicarbonate. We actually need the bicarbonate, so let's not pee it all out. Okay, take as much back as you can because we need to mop up all these extra H plus. So the buffer working together with the proximal tubule, that's going to help regulate your blood pH. Okay? And actually your breathing is gonna help with regulating blood pH as well, because we breathe out carbon dioxide, right? Okay. So the more carbon dioxide we breathe out, we can also help increase the pH that way. Questions? Okay. Poll time. All right. That was a minute. Got half the answers in. Things that are not found in filtrate include proteins, they are too big, and cells. Right? That's why you should not have blood in the pee, right? Because the red cells are all supposed to stay inside the nephron. Sorry, inside the blood and not in the nephron. Okay, which of the following processes involve moving substances from filtrate into the blood? Filtrate into the blood. So that means you're taking it back, you're putting it back into the blood. That would be absorption. Absorption. Okay, next we have the loop of Henle. The loop of Henle. The loop of Henle, as you know, has the descending limb that goes down to the medulla and the ascending limb that comes back up. The main function of the loop of Henle is water absorption, as well as sodium chloride absorption. So on the way down, we're going to be absorbing water, and on the way up, we're going to be absorbing sodium chloride. And to help you understand that, I am going to give you another note. So reabsorption at the loop of Henle. Reabsorption at the loop of Henle. Now, to help you understand this, I'm just gonna give you like some numbers again. Okay, some numbers. So this is the proximal tubules. Okay, and then we're gonna be going down. We're gonna come back up again. And then this is like the, cortex. And this is the renal medulla. Now, we measure the concentration of a fluid. Concentration of a fluid. Okay, we call that like osmolarity, right? Osmolarity. Osmotic pressure, right? You remember that from lecture 1. So in the proximal tubule, we already take back a lot of stuff. A lot of water, a lot of the NaCl, 60 to 70%. 60 to 70% reabsorption. So by now, I'm just saying, totally making this up. This is about 400 units of osmolarity. Okay. So then, do you remember I tried to tell you the renal cortex and the renal medulla, like which one is more salty? Do you remember that?
Renal medulla is more salty.
That's right. So I'm gonna use like maybe another color, like red color here, to show the concentration outside. Again, these numbers are, they're just kind of random number. I mean, they are close to the real thing, but don't get too hung up on them. Okay, so 600, and then it gets more concentrated the deeper we go, right? 1,000, 1,200, and maybe 1,400. Okay, so right now the filtrate, which is what's going to become the urine, I keep on telling you that it's kind of diluted at this point. It's just about 400. So this here is the descending limb, right? Descending limb. Going down is the descending limb. So let's put an okay, descending limb. Descending limb is only permeable to water. Only water can pass through. So we got the filtrate coming in from the proximal tubule, and now it's going down the loop of Henle. The concentration of the filtrate is 400, but the surrounding area, in the renal tissue, is 600, and only water can move. So which way will water move? Is it going to move into the nephron or out of the nephron? Is it going to move towards the 600 or move towards the 400? Talking about the water. You guys don't remember this from before? Where does water always go? Towards the saltier end or the less saltier end?
From
More
high.
salty. Water go to the more salty.
Yeah.
The water goes to the
From
more
low to
salty.
high.
That's right, to the saltier end, right? Yeah, like you remember I said you put a spoon of salt in the mouth, it sucks your saliva out, right? So that's what happens, right? The water is gonna move out. Water is gonna move out. Okay. Then what happens to the filtrate? Well, the filtrate is gonna be a little bit more concentrated now. A little bit more concentrated. It's gonna become like 600. It's gonna continue to go down. But as the filtrate moves to the next section, goes deeper into the medulla, the surrounding is now 800. Right? So more water will be absorbed. That's why it needs to be saltier and saltier as we go down the deeper and deeper into medulla, because you need to always be higher than the concentration of the filtrate in order to keep on drawing the water out. Okay? So afterwards, this will become 800. And then the filtrate is going to be like even more concentrated now. Even more concentrated. Okay? And then you're going to absorb more water. And ultimately, when you get to the bottom, like this is really concentrated stuff. Right? Really concentrated. Do you understand? Like 1200. And so you're basically going to be absorbing as much water as possible. So a couple of things to note here. H2O is absorbed by osmosis. Concentration of filtrate increases as it goes down the descending limb. So it's the most concentrated at the bottom. Now, we are not the only ones who have kidneys, okay? Mammals, they have kidneys, okay? So if the organism lives in a very dry environment, like the desert or something, they need to conserve more water. If you think about like a dolphin also has kidney, okay? They live in a very salty environment and say that they need to conserve fresh water in the body. So do you expect their loop of Henle to be longer or shorter or same as us? For organism that lives in hot or salty environment like the ocean, if their body needs to conserve more water, do you expect their loop of Henle to be longer, shorter, or same as us?
Shorter.
Why is that?
Because here, as you go down, it becomes more and more salty, right? So if it's shorter, then the more like normal water will stay. No, I don't think that's right.
Okay, sorry. You said as it goes down, it becomes more and more salty. What's the it?
The loop of Henle, the filtrate becomes
The
more
filtrate.
salty.
And what does the filtrate become eventually?
P.
The P, right? Okay. So if you want to conserve water, do you want your P to be concentrated or do you want your P to be diluted? If you want to conserve water. Let's think about that. If you want to keep as much water in the body as possible, do you think it's good to produce very concentrated, like yellowish pee, or like really diluted pee?
Diluted.
That's the other way around, guys. If you want to conserve water, your pee should be very concentrated, right? Concentrated means it doesn't have a lot of water in it, right? Make sense? If you want to conserve water, you want to keep the water in the blood and not in the urine, right? Not in the pee. Am I making sense here? Or am I missing something?
Sir, I thought your pee shouldn't be concentrated. That's why you're supposed to drink more water.
Okay.
So,
No, you're right. Okay. But we are talking about a different thing here. Okay. I am saying if you don't have a choice, okay, let's in the desert, right? You don't have access to a lot of water, right? Fresh water. So your body is gonna want to conserve water. Are we all on the same page with that? In a situation,
Yeah.
okay. In a situation where you don't have a lot of water available, your body wants to conserve water, right? Okay. And to conserve water, that means your pee needs to be more concentrated than normal. Right? Like, I don't mean to be gross or anything, but then, in the morning, the color of the urine is typically darker than, during the regular day, right? That's because we haven't been drinking water throughout the night while we're sleeping. And so your body's actually conserving water for you, and therefore the urine is more concentrated. There's less water in the urine, right? Now, assuming you understand all that, back to my question, for organism that lives in like hotter environment or like in the ocean where they try to conserve fresh water in the body, they need to have a longer. The answer is longer. If you see the quiz question, choose longer. Okay, longer loop of Henle. Why? Because the longer the loop of Henle, the more water you can take back from the filtrate. If the loop of Henle is really short, you don't have a lot of time to absorb all the water. It's just gonna end up, in the pee, and then you're just gonna lose all the water out of your pee. Do you guys understand this?
Yeah, I got it.
Yeah. Anyone else have any questions about what I said? So, Patrice, back to your point, like that's why we need to drink a lot of water so that our pee is not like concentrated, right? Basically when you see the urine being concentrated, it's an indicator that you haven't been drinking enough water.
that you're like dehydrated.
Yeah, exactly, right? Because if you're well hydrated, then your body doesn't need to conserve water, and then you just pee out, as much as you drink, and your urine is gonna be, not as concentrated, right? Have a very light color to it.
I have a question.
Hmm.
So can you just repeat the part about like the loop of Henle being shorter? It's not enough time to
Yeah, so look here,
reabsorb,
right?
right, the
For
water?
example, like at this particular length, just, figuratively speaking, we can absorb 8 water molecule, right? I've drawn 8 H2O there. You agree? Now, if I make it shorter, let's say the loop of Henle ends right here and it goes back up, then I only have time to absorb 2 water molecule. You know what I mean? Like the longer it is, the more water I can take back because, it takes a longer time for it to pass through the loop, right? Does that answer your question?
Yeah, thank you.
Okay. Now I'm gonna tell you another thing here, okay? I know it's already very confusing, but listen. Hopefully this will shed more lights to the understanding. Coffee. Right? What does coffee make you do? For those of you who drink coffee or like you used to drink coffee or you drink any kind of caffeinated drink, you drink coffee, what does it do to your body? Like in terms of, going to the bathroom.
Makes you pee.
Oh,
And the
diet?
other one.
Yeah, it makes you pee, right? You drink coffee, you just have to pee. It's a diuretic. Diuretic. Okay. Now just you don't have to write these things down. You just listen to me and try to understand. So you drink the coffee, there's caffeine in the coffee, there's caffeine in your Red Bull and whatnot. And we do not have a carrier in the proximal tubule to take back the caffeine, right? I told you that already. So all the caffeine that gets filtered out, it's gonna stay in the filtrate. So there are extra dots in the filtrate now. What is that gonna do to the number here? What is that gonna do to the number? Is it gonna be higher than 400, lower than 400, or same as 400? Okay, you got all these extra caffeine in the filtrate that you were not able to reabsorb. Higher, lower, or same?
Would it be higher because it's gonna be increasing like the amount of stuff in there?
Exactly,
filter.
right? It will be higher because there's more stuff, there's more caffeine, there's more solute. So the number is going to be higher, right? Now don't do this to your diagram. Just let me do it. I don't want you to ruin your diagram. So it's going to increase it. I don't know. I'm totally making this up. Let's say increase it to 800. Let's say you drink a lot, right? So now the 800 is going to move forward to here. And remember, this is osmosis. Okay, and you guys were saying the water goes towards the higher end, right? So if it's actually 800, instead of reabsorbing water, now you are pulling water from the surrounding. Instead of taking water back into your blood, you are losing more water into the filtrate, right? I mean, later on, you will still probably be able to absorb some water, but the point is, because of the extra caffeine in the blood, it got the osmolarity to be higher in the filtrate, and as a result, you don't get to absorb back as much water. And that's why it makes you pee more. It's a diuretic. It actually dehydrates you, right? Remember I told you about that story of, people mixing alcohol with Red Bull, and then at the end of the night, they actually, have to go to the emergency, or some people actually die because of that. That's because the alcohol combined with the Red Bull really dehydrates the person because of this. The caffeine stays in the in the filtrate, draws the water from surrounding, and you end up peeing it out. Even though you're consuming liquid, right? But there's too much caffeine. It's just drying you up. And it doesn't have to be just caffeine. Same thing with diabetics. Okay? The glucose, if all the transporter are working at full speed, you cannot absorb all the glucose back into the blood. And so the glucose stays in the proximal tubule, continue moving on, and the number is going to be higher. The number is going to be higher. Right? And when the number is higher, what happens? You draw water from the surrounding. Okay, and then you end up peeing it out. Right? So frequent urination is a symptoms of many things, but also of diabetes. Okay, one last story. You ever hear people say, like, if you're stranded in the ocean waiting for help, even if you're super thirsty, you cannot drink the salt water, right?
Yeah.
Yeah, you drink the salt water, you actually will die. And the reason you probably would understand now, if you drink the salt water, the number in the filtrate is gonna be like super high now, right? Maybe it's gonna be 1,000 instead of 400 over here, right? And then it basically is just gonna destroy your kidney. It will draw all the water out from it, and then you will end up dehydrating even quicker. Okay, so a lot of things you can understand now just by thinking about the numbers. Okay, the numbers in the filtrate will change, but the numbers in the surroundings, they don't really change too much.
I have a quick question.
I think I know what it is, but go ahead. Yeah.
Okay, so here in the bottom, the 1200 and 1200 is the same.
Mm-hmm. And
So
then
if it's
it's
the
gonna
same,
become
it'll
like,
still go out? Sorry.
oh, it's like 1400 here, right? So like,
Oh, but it's beside the 1200 on the
yeah,
descent.
it's probably just like the way I've drawn it, like maybe shift shift it a little
Okay,
bit
okay.
forward. Yeah, yeah. So those of you who have a very keen eye, you might think you might wonder, like, if this keeps on going, like, I understand why the black number is gonna go up because you're losing water, right? But how about the red numbers? Right? You might wonder, like, how come the red numbers don't go down? Right? Like, how come the 600 here does not become like 500, and then how come this doesn't get diluted? Would your kidney just get diluted over time? Well, that is an excellent question if you're thinking about that. And that's where we have to look at the ascending limb. Okay, so in the ascending limb, NaCl are absorbed by active and passive transport. And water is not absorbed here. Okay, water is not absorbed here. So you're gonna have some transporter here on the side. Na plus transporter. And Na and Cl, they are always together, like traffic and weather. Right? When Na goes, Cl is gonna follow it. So this stuff's gonna come up. This stuff's gonna come up, and we're gonna absorb the NaCl. So NaCl is gonna go. You're gonna absorb the NaCl. And when that happens, the filtrate will get diluted. Right? We'll go back to like 800. Okay, and then we're just gonna dilute it. And then you're gonna absorb more NaCl. I'm not gonna draw all of it. You get the point, hopefully. Keep on taking it back. Okay. And then eventually you're just gonna go back to, about 300 to 400. Like depends on the body's need. Okay, sometimes you need to take more NaCl. Okay, so like 600, right, 400, and then it just goes back up. So because we are taking the sodium chloride, that kind of balances out the water. Okay, so it's not gonna, like, you're not gonna dilute the kidney. Yeah, you're diluting it on the left side, but that's okay. You're also like making it more concentrated on the right side. So the two kind of balance each other out. I mean, it's a little bit more complicated than that, but like I skip some details that we don't have to know, but that's the gist of it. Yes,
So I
Blessing.
have a question.
Yeah.
You know how you said the body doesn't absorb caffeine?
It doesn't absorb it from the filtrate. Doesn't absorb it from the filtrate. But go on, yeah.
And then in one of our previous classes, you said adenosine as their neurotransmitter.
Yes, okay.
So if the body doesn't absorb caffeine, so how is it able to do all this adenosine
Yeah, no, I
neurotransmitter?
understand. I think when I say absorb, okay. So you are thinking absorb as in like absorb it from the food into the blood, right? That happens, of course, right? So when you drink coffee, coffee goes into your stomach, and then your body absorbs it, and it goes into the blood, right? And then it does
Okay.
all the things, like it wakes you up, it gets you all jittery or energized.
Yes.
That's the absorption that you are thinking of. The absorption I'm talking about is now that you have all these caffeine in the blood, right? The blood goes to the kidney, okay, and then you filter all of it. You filter the blood in the glomerulus, right? And then it goes into the Bowman's capsule. Okay, so now the caffeine is in the filtrate. In the filtrate, you understand the filtrate, right? Like it's inside the nephron now, right?
Yes.
Once it's inside the nephron, you don't take it back into the blood. That's what I mean in terms of you don't absorb it, right?
Okay. Okay.
Once you lose it into the urine, there's only one way to go. It's going to end up in your pee. You're not going to be able to take it back up anymore. Okay?
Makes sense now. Yes.
All right.
Thank you.
Very good. So, in the loop of Henle, you will absorb an additional, 10-15% of the filtrate. Again, like I don't know if the numbers are helping you guys, but like I said, right? Like, of the 120, you take back 60 to 70% in the proximal tubule, and then you take back an additional 10-15% from the loop of Henle. Water on the way down, sodium chloride on the way up. So the filtrate, the concentration of filtrate decreases as it as in the filtrate goes up the ascending limb. All right, that is that. Let's take a break here. We still have quite a long way to go. So let's come back at like 9:46. Okay, see you in a bit. Okay, let's keep going. So now that we finished going through the loop of Henle, we absorb pretty much, 80 to 85% of everything that was lost in the filtration process. Okay, so again, 60 to 70% in the proximal tubules, additional 10-15% in the loop of Henle. Now we're in the final stage. We've pretty much taken back most of the stuff that we wanted to keep. So we're gonna move. Oh, sorry, I forgot to show you. This is basically what happens. Okay, so what I did not show you in my note is that after you absorb the water doesn't really stay in the kidney. Okay, remember there is always that peritubular capillary right next to it, and so it just stays in the kidney briefly, and then it goes into the blood. Same thing with the sodium chloride, right? It just goes into the kidney briefly, and then it goes into the blood. And that's what's happening in the loop of Henle. Okay, it says vasa recta here. That's just like the special part of the peritubular capillary that's next to the loop of Henle. Okay, this is like nothing to it. All right. I basically just I've done this so many times that sometimes what I say is essentially what's on the slide. So by the time the filter reaches the distal tubule, roughly 80 to 85% of the water and the solute have already been absorbed. So at the distal tubule and the collecting duct, this is the place where we do final adjustment of the urine content. Okay, this is where we fine tune it. If there is still stuff you want to get rid of, now is the time to secrete it here. If there is still stuff you want to conserve, now is the time to take it back. After the distal tubule and the collecting duct, that's it. Okay, the urine is going through the ureter, and it's not coming back. All right, this is the final stop to make adjustments before the point of no return. Okay, as soon as it goes to after it passes through the collecting duct, it's going to go to the renal papilla, right? And then the minor calyx, major calyx. And so beyond this point, no more adjustment is possible. Okay. So most of the things are not going to be able to pass through on their own. Right? It's impermeable to solute, and the adjustment can only be made through active transport. And these transporter often is going to rely on hormones to help regulate what to take back and what to get rid of. And we're going to be learning about 3 of these hormones shortly. Okay. But the point is, at the distal tubule and collecting duct, fine adjustment. Okay, final stop. Okay, so next we are going to talk about the regulatory function of kidneys, specifically water salt balance. That's a really big note. We're going to talk about conservation of water, as well as there's something else. Okay, I don't remember. We're going to get there. Okay, so these are some drugs that people take when they have high blood pressure. If you or someone who has high blood pressure, you might be familiar with these drugs, even though you might not be taking exactly these kind of medication, but they belong to a group of medication called diuretics, which helps you pee, and then there's something called ACE inhibitor, ACE. Okay, ACE inhibitor. These are the 2 primary kinds of drugs that helps you lower blood pressure. And as you will see shortly, that the kidney actually plays a key role in lowering blood pressure. So this next note is called the RAS, RAAS. It's a long one, okay? Yeah, I mean you can, I don't know, like if you have the study guide, you can fill it in. There's a box for this RAS stuff right here. Question 8: use a flowchart to illustrate how the role of RAS in maintaining the blood pressure. Okay, but I'm just gonna do it in the note, so I have more space and I can post this all in one thing. And so this is RAS, RAAS, which stands for renin, angiotensin, aldosterone, system. renin angiotensin. Angio, like, you know, your angiogram. Number 10, sin, and then aldosterone. Aldo, like the shoe brand. Sterone, like testosterone, progesterone. It's a steroid hormone. So the RAS system. So like I would start here, and then I would go like here, and then I would loop back like that. That's generally how it goes. Okay, in case you're planning for space. Okay. What does it do? The purpose of the RAS is to what do we do here? Let me think about this. This is gonna lower blood pressure. Oh, sorry, no, this is not lower blood pressure. This is increased blood pressure. Confusing myself for a second. Increased blood pressure. In other words, we need to activate RAS when our blood pressure drops. Okay. If your blood pressure is dropping, you gotta activate the RAS. So tell me, why might your blood pressure drop? Why?
Need a sugar, maybe sugar level of sugar going down.
Okay. Yeah, that's a common thing for people to say, actually, but not necessarily. Not necessarily. Sugar doesn't really have much to do with the blood pressure. Anyone else? Like nothing fancy. Okay, it's something that is it could happen to any of us.
Maybe more nervous.
Maybe what? Mount Everest? Did you say?
Nervous, yeah.
Okay, but we don't. It's just something simple. It's something that happens in everyday life. Okay.
Okay.
Loss of
Standing
blood.
up too quickly.
Okay, yeah. If you stand up too quickly, you know, gravity pulls your blood down from the head, and you feel a little bit lightheaded. But that's like really brief. Okay. Anyone else? I saw someone else who wanted to say something.
Loss of blood.
Yes, there we go. Loss of blood. Okay. If you bleed, if a person bleeds excessively, they are gonna lose blood pressure just because your blood volume go down, right? Okay. So what else? What else could cause your volume to go down? Someone already mentioned it earlier. I think it was Patrice or maybe someone else. Heart problem, okay, yeah, sure. Dehydration, okay, dehydration. Right? If you're dehydrated, your blood volume goes down. Blood volume goes down, your blood pressure is gonna go down. Okay. All right, moving on. Now, hopefully you know what I'm drawing. I will be a little bit heartbroken if after all this time, you still don't know what this is. Okay, what is this?
Glomeralis and the Bowman's capsule.
That's right. Glomerulus Bowman's capsule. Now, what I did not tell you is that located next to the glomerulus, there is like a group of special cells. Okay, some special cells right there. Okay, these special cells, it's called It's called that. Okay, juxtaglomerular apparatus. Juxta means next to. Apparatus means like a group of things. So it's a group of cells that's next to the glomerulus. Okay? Thankfully, we can just call it JGA for short. So this is basically like what this thing does is it's a BP monitor. BP monitor. Okay? So as the blood is going into the glomerulus, the JGA is gonna check for the blood pressure. Is it where it should be? Is it too high? Is it too low? Okay, it's basically a detector. So if you have a drop in blood pressure, the JGA is going to detect that. And in response to a drop in blood pressure, JGA releases an enzyme called renin. I'm just gonna do it in blue. So that's the R in the RAS. It begins with the renin. So far, so good. Like not too complicated, right? I hope. Any question? Okay, let's move on to something else for a second. Anybody know what this organ is? I'm trying my best here. What's this organ?
Liver.
Yeah, it's very good. Very nice. This is liver. Liver makes a lot of proteins, plasma proteins, okay? And this one makes something called angio number 10 sin, like when you do something bad, angiotensin ogen. Okay, this is a plasma protein. Angiotensinogen. What does ogen mean? Do you remember that? Long time ago when we first met at the beginning of the semester. What does ogen mean? Like fibrinogen or like pepsinogen. What does ogen mean? Okay. Ogen means inactive, right? You gotta, for example, like in the digestive system, the pepsinogen has to be activated into pepsin by HCl. That's something you should know for the test. Before the fibrinogen has to be activated into fibrin. So here, angiotensinogen is inactive. Okay? And what it does is, in the presence of renin, it's going to get activated. It's going to get activated into. Anybody want to guess the name? Probably know it already, right? Angiotensin 1. Okay? So that's like the A right here. ROS, right? The A is the angiotensin. But this is number 1. So right now in your blood, you probably have the angiotensinogen, unless like you are dehydrated or something, like unless your blood pressure is low. But otherwise the angiotensinogen is going to stay as angiotensinogen. It's going to stay as the inactive form. It's going to stay inactive unless you have renin. Right? And you're not going to have renin unless you have low blood pressure, right? Okay. So there is going to be the angiotensin number 1. Okay, we're going to have another organ here. Another organ. Organ. This one I'm sure you know. The lungs. Of all places, the lungs. The lungs is gonna produce an other enzyme. And this other enzyme is called angiotensin converting enzyme, or ACE for short. Angiotensin converting enzyme. And what is it going to convert? Well, it's going to convert, as the name implies, it's going to convert the angiotensin, number one, into angiotensin, number two. Okay. Now let's backtrack a little bit. What's the problem right now? What's the problem we're trying to solve in the body right now?
The drop in blood pressure.
That's right. So how do we fix that? If our blood pressure is dropping, should we squeeze the blood vessels or should we make the blood vessels bigger? Blood pressure is dropping. Should we squeeze the blood vessel to help or should we make the blood vessels bigger to help?
Squeeze.
That's right, we're gonna
Mm.
squeeze them. So that's what angiotensin number 2 will do. Angiotensin number 2 is gonna cause vasoconstriction. Okay. You're gonna squeeze the blood vessel. Okay. Makes blood vessel smaller. Squeeze them up, people. And that's gonna hopefully increase the blood pressure enough. But sometimes that's not enough. Right? Which is why this is gonna go to another place. Right? What is this thing? Anybody remember this guy?
The kidney with its hat.
That's what hitting with the head, but what's the head? Do you remember that one? That's where the adrenaline comes from. So it's named after that. That's okay. This is the adrenal gland. Okay. So the angiotensin number 2 is going to go to the adrenal gland. Actually, it's going to be the adrenal cortex, the outside, and it's going to trigger it to release aldosterone. Aldosterone. Okay, so the ROS system is renin, angiotensin, aldosterone system. It's going to trigger the release of aldosterone. Aldo like the shoe, sterone like progesterone, testosterone. It's a steroid hormone. So this is a steroid hormone. Okay, so what does aldosterone do? Aldosterone is going to go to the nephron. It's going to travel through the blood and act on the kidney. And travels through the blood and acts on the kidney. So what does it do? Well, this is the distal tubule and the collecting duct. This is the blood vessel, okay? The peritubular. capillary. Okay, so you have all these. The black dots are like Na plus and Cl minus. Okay, so I'll let you catch up first, and I'll tell you what it does. That's a comma. Okay, that's a comma. So remember, at the distant 2B and the collecting, that's where you do the fine tuning, right? That's where you do the final adjustment. And in the presence of aldosterone, we are going to increase sodium and chloride absorption. Right. So the sodium and the chloride will go back to the blood. That's step number 1. So that means you're going to make the number a little bit higher in the blood now, right? The osmolarity higher. By doing so, water will follow. So increase H2O absorption as well. Okay, the first one is active transport, and then the second one is passive, increased water absorption. Because the sodium chloride is moving into the blood, the water get pulled along with it. Water always goes towards the saltier end, right? So what's going to happen to your blood volume now that you have more water in it? It's going to go up. And when you have more blood volume, your BP also increases. Okay, so that's how the RAS system works. Okay. The angiotensin number 2 squeezes the blood vessels, which increase the blood pressure. And then it triggers the release of aldosterone, which helps you conserve water and sodium. And that will further increase your blood pressure. And collectively, these things are gonna basically counteract the drop in blood pressure. Okay. Any questions at all? This is a lot to take in. Just gonna give you a moment to think about it. Any questions at all, people? Okay. Everything needs to be balanced in the body to maintain homeostasis, right? So this is what we need. The RAS is what we need when we have drop in blood pressure. So what's going to happen if the opposite happens? If the opposite happens. Right? So if the opposite happens, we're going to need another hormone. Let's draw that in, hot pink here so it stands out. Right? So let's say you have, this one is very quick, okay? Let's say you have increase in blood pressure. Increase in blood pressure. Okay, your blood pressure is too high now. And that could happen for various reasons. Right? Like, you constantly stressed out. Your blood sodium level is way too high. Then, this is the heart. There's so many organs here that's involved, okay? So the heart, in the atrium of the heart, there's a cluster of cells that will respond to high blood pressure. In the event of high blood pressure, it releases a hormone called atrial natriuretic Uretic. That's natriuretic hormone. Okay, ANH, natriuretic hormone. So it does a couple of things to bring the blood pressure down. Let's go through the easiest one to understand first. When you want to bring the blood pressure up, the aldosterone is going to increase sodium absorption, increase water absorption, and then because you have more water in the blood, you're going to increase the volume, increase the blood pressure. But when you want to bring it down, then ANH is basically going to go to the kidney, and then it's going to reverse all these things. It's going to does the opposite. It's going to reduce NaCl absorption, which will reduce H2O absorption, and then blood volume goes down, and blood pressure goes down. Okay. So it's gonna basically encourage peeing. It's gonna encourage you to get rid of more water so that you don't have as much in the blood. It brings the blood volume down. But that might not be enough. So ANH is also gonna go and prevent aldosterone from being released. I hope you're using a different color, otherwise it's very messy. It's already very messy. And it also goes and block renal. So essentially, ANH is gonna turn off the RAS, and at the same time is gonna encourage you to pee out more water. And together, these actions gonna lower your blood pressure. So essentially, the RAS system and the ANH, they are like two ends of the balance, two ends of the seesaw. They have to work together to maintain optimal blood pressure. If it's too high, ANH brings it back down. If it's too low, the RAS will bring it back up. Now, sometimes this is not enough for people who suffer from chronic high blood pressure. Like, chronic, chronic means like ongoing, right? Ongoing high blood pressure. Then even the ANH is not enough to bring the blood pressure down. And that's why the person has to take the diuretic, right? Now you understand. Diuretic means it makes you pee more. By peeing more, you lower the blood volume, you lower the blood pressure. And also, the person might take the ACE inhibitor, right? So ACE inhibitor. That's not a nice color. Whatever, I'm just gonna use blue here. ACE inhibitor. Okay, this is medication. And as the name implies, the ACE inhibitor is gonna inhibit the ACE. And when you inhibit ACE, you essentially are shutting down the RAS. Okay. Without ACE, number one's not gonna get converted to number two, and then the rest is not gonna happen. Make sense? Questions? All right, I do have a bunch of questions for you. Some of these will show up on the test, okay? So I mean, on quiz number 3. When is quiz number 3 anyways? Does anybody remember? I should keep better track of my, let me take a look. Quiz number 3 is, yeah, quiz number 3 is April 1st. No jokes. April 1st is in 2 weeks. So you're gonna do the test next week, and then you're gonna do the quiz on April 1st. All right. So make a note of that here. Let's do this one. Which of the following activities would trigger the ROS? What do you think? Just one answer, okay? One answer. Like if it's multiple answer, it would say, choose all correct answers, right? Okay, anyone else? All right. So we turn on the RAS when you have low blood pressure. Low blood pressure is brought on by blood loss or dehydration. So if you drink several glasses of water, that's not gonna trigger the RAS. Drinking water is not gonna make you dehydrated, right? Shoveling the driveway for an hour on a cold winter day. Sure, it's tiring, but you're not gonna be sweating too much, right? Because it's cold winter day. So if you're not sweating too much, you're not gonna be dehydrated. Probably not gonna trigger the RAS. Mowing the lawn for an hour on a hot summer day. That's gonna make you pretty sweaty. Okay? You might be a little bit dehydrated afterwards. That's the answer. Okay. Eating 4 slices of pizza, that's fine. I mean, there's some sodium, but the effect is not as immediate as, sweating, right? Sweating, you're really losing the fluid immediately, right? So the answer is C. Okay, next one. Okay, well, let's talk about this. High level of ANH. ANH is the one that's from the heart. Let's take a quick look here. ANH is the pink one. And it's gonna basically makes you pee more. It's gonna be also, excuse me, it's gonna be also suppressing the RAS. And so increase aldosterone level in the blood. No, it will decrease it by releasing, blocking its release. It will increase the blood pressure. No. Increasing blood pressure is what triggers the ANH to be released. Decrease Na plus level in the urine. That is also not true because you want to pee it out. You pee the sodium out, sodium will draw the water with it. Increase Na plus level in the blood. Now you want to take the Na plus and put it in the urine. Increase urine volume. That's the right answer. Okay. So like that's why I said like this is a difficult quiz. And that's why I'm giving you 2 chances to do it, right? Okay, next question. This is really hard. If the level of renin in blood is high and ACE is low, which of the following is correct? Okay, so let me show you how to do this one. We have angiotensinogen, and then it becomes NGO1 and NGO2, right? This one needs renin, and this one needs ACE. So the question is asking, what if you have a lot of renin and not a lot of ACE? What's gonna happen? Right, think about that first. I'm not gonna do the polls. There's only 3 or 4 people doing it. There's no point. You think about it, and I'll explain to you. Okay, so we have high renin. We have high renin. So that means angiotensinogen is going to get converted into angiotensin number 1. That's no problem. But we have low A's, right? Low A. So basically it's like, very little. So angiotensin 1 is going to be stuck. I mean, some will get converted, but we don't have enough A's. So we will not be getting a lot of NGO2. That's why there is going to be low angiotensin number 2 because we don't have enough A's. We're going to have a lot of NGO1, right? Because the NGO1 has nowhere to go. There's not enough A's to convert it into number 2. Right? So you're going to have a lot of 1s. And angiotensinogen, yeah, it's going to be low. It's going to be low. Because renin is there, right? So it's basically going to convert all of them into NGO number 1. So the answer is low, high, low. Which is which one? Which is D? Anyone want to ask me anything before we try another one? Okay. Here's another one. So for the benefit of the 5 people who usually do the poll, I'll launch it. See if you guys get it right. Okay. Thank you. Let's take a look again. So we have the angiotensinogen. Okay. 1 and 2. I'm just getting lazier and lazier. We need the renin and we need the ACE. So We don't have enough renin. Don't have enough renin. We have a lot of A's though. So let's see. Angiotensinogen, because we don't have enough renin, they have nowhere to go. Right? Some will get converted, but most will stay as it is. So that's going to be high. Okay. So we're not converting the angiotensinogen into 1. This is going to be low. And if you don't have a lot of 1 available, it doesn't matter. You have a lot of A. Right? You're still going to have low levels of 2. You don't have enough raw material. It doesn't matter. You can convert it. Like, you just can't do it. It's like the supply chain issue, right? You don't have enough 1, then you won't have enough 2. So the answer is high, low, low, which is B. Okay, so expect these questions on the quiz number 3. Right? So another hormone. This one is called anti-diuretic hormone. Diuretic means to pee, right? To encourage you to pee. So this is anti-pee hormone. It helps you conserve water. And how does it do that? Well, it's going to act on the distal tubule and the collecting duct, and you want to conserve the water in this case. The ADH is made in the hypothalamus, which you remember, right? Hypothalamus is part of the brain. You should know it for the test. It's, thalamus, right thalamus, left thalamus. You have the third ventricle in the middle. Then you have the hypothalamus at the bottom. Dangling from the hypothalamus is the pituitary gland. So ADH, anti-diuretic hormone, anti-P hormone, is made in the hypothalamus, and then it's stored in the back of the in the back of the pituitary gland. Okay. More on that later on. Okay, but that's all you have to know for now. And what it does is it helps control the blood concentration by absorbing water. If your blood is too concentrated, then you need to absorb water, right? So when a person is dehydrated, the blood osmolarity increases. Right? So look, this is the hypothalamus. Okay, hypothalamus. These are cells in the hypothalamus. You don't have to draw this. You'll understand soon. This is hypothalamus. And you have all these fluid in the surrounding. So if the blood osmolarity is high, okay, that means there's a lot of dots outside, right? And I taught you this last semester. In this environment, in a hypertonic environment, water will leave the cells. Okay. When the cells of the hypothalamus shrinks, because of this, water action, it shrinks, that sends a signal throughout the brain that makes you feel thirsty. It's, I feel dehydrated, I'm thirsty, I should drink. Drinking water is going to help, right? It's going to dilute your blood. But shrinking of the hypothalamus also sends signals to the pituitary gland and tells it to release the ADH. We are really dehydrated right now. Let's not pee too much. Let's conserve the water. Conserve what we have. We'll continue to get rid of the toxin, no problem. But, keep as much water as possible. So that's what happens. I'm going to just show you this instead of drawing it out. I think we had enough drawing for one day. There's the hypothalamus. Okay. And when the blood osmotic pressure, the blood concentration goes up, right? Because of dehydration, excessive sweating. Now you might be thinking, hey, isn't this also the trigger for RAS, right? Like when you're dehydrated. Yes, like a lot of things are overlapping. Your body, it's not just like doing one thing or the other. There's like, complementary processes that happens at the same time to achieve the same goal. But on that note though, like if it's just blood loss will trigger the RAS, but not ADH. Because losing blood does not change your blood concentration, right? Like if you have a can of Coke, you pour out half of it, the rest has the same concentration as the original, right? So like if you're losing blood, you're not changing your blood concentration, and this ADH is not going to be triggered, but the RAS will be triggered. Anyway, so if you're dehydrated, if you're sweating, your blood concentration is going to go up, and that's going to trigger the osmoreceptors, the one that shrinks. That creates thirsty behavior. You drink water, and drinking the water will replenish your fluid level, and your blood osmolarity will be brought back to normal. At the same time, the shrinking is going to cause the hypothalamus to send a signal to the pituitary gland, and that will release the ADH, the anti-diuretic hormone. It travels through the bloodstream to the distal tubule and collecting duct, and it absorbs water. Okay. Increase the water absorption of the kidney, basically, to prevent further dehydration. It's probably easier to understand like this. On the left side, we have the absence of ADH. When you're well hydrated, when you have plenty of fluid in the body, okay, we can see the dot represent the osmolarity, right? So on the way down the loop of Henle, because we're absorbing the water, it gets more and more concentrated. Remember the picture we drew? Right? It's like get more and more yellow until it's like dark brown at the bottom, right? And on the way up, because we are absorbing NaCl, it gets diluted. So without ADH, that's it. Right? Whatever you get coming out of the loop of Henle, that's the P that's going to be coming out, and we're going to producing large volume of diluted urine. Okay? Very light color, lots of P. On the other hand, if you are dehydrated, then your pituitary gland will release the ADH. Same thing happening in the loop of Henle, no changes. But then we are going to be absorbing water in the distal tubule and the collecting duct, which normally does not happen. But in the presence of ADH, anti-P hormone, right? Anti-diuretic, you need to conserve the water. So you take out as much water as you need, as you can, and then you produce small volume of urine. Okay, it's not possible to not make urine because we need to get rid of the waste from the blood, right? So it's not about not peeing at all. You still need to pee. Peeing is an essential mechanism, but you can control how much water is in the pee, right? So the more water it is, the more diluted it's gonna be. Okay. All right, this is a long one. I'll just do it for you. Diuretics are drugs sometimes used to treat individuals with hypertension. I told you that already, right? To make you pee more. These drugs inhibit reabsorption of Na ions by the loop of Henle. What effect would this have on osmolarity in the nephron? Okay, so look here. You absorb the NaCl on the way out, right? Diluting your filtrate. And what happens here is the diuretic blocks the absorption of Na. Okay? So what happens? Let's see. Osmolarity would be higher than normal in the collecting duct. Osmolarity would be higher than normal in the descending loop of Henle. Osmolarity would be lower than normal in proximal tubule. And then osmolarity would be lower than normal in collecting duct. Okay, so let's take a look at the question again. It says the drug inhibit absorption of NaCl in the loop of Henle. So the drug is having an effect right here. Right, so if you're not absorbing NaCl here, what's going to happen to the filtrate? Well, it's just going to be like, I should change it back to black, I suppose. It's just going to be really, really concentrated here as well. right? Like because you're not taking the sodium chloride stays in the filtrate. Okay, and it's gonna stay in the filtrate like all the way. Okay, it would have no effect on the proximal tubule. It would have no effect on the descending limb. Right? But the filtrate will be more concentrated in the distal tubule and collecting duct. So that's the answer. Okay, no effect on the descending limb, no effect on the proximal tubule. And there are more dots, there are more sodium chloride because you're not taking it back. The drug is blocking it. Okay. And so all the sodium that's in the collecting duct and distal tubule will actually suck water from the surrounding, making you pee more. And that's ideal if you have high blood pressure. You want to pee out. So I'm just going to go through a few conditions with you. First one is diabetes insipidus. This is not related to, type of diabetes that people are familiar with. And this is a situation that happens when the hypothalamus no longer produce ADH. Okay, the cells that produce ADH in the hypothalamus, they're destroyed for whatever reason. Okay, and without ADH, that's actually a pretty big problem. Remember, ADH is anti-diuretic, right? It's anti-pee, right? So without ADH, the person pee all the time. In extreme cases, they pee as much as 20 liters per day. So they will get severely dehydrated if they don't replenish the fluid. They have to drink a lot. So sometimes they have to take replacement hormone medicine, basically to reduce to replace the missing ADH. So diabetes insipidus. If your kidneys are not working anymore, then you need to get a kidney transplant. But kidney transplant is not readily available. It's the most it is the organ that has the longest wait list in the transplant. So while you wait for the kidney transplant, the only thing you can do is to do dialysis. So there are two types of dialysis, and it's just very briefly. Okay, hemodialysis, you take the blood out and then you filter it. So this one you have to go to the clinic to do it, right? So using similar process as like osmosis, the blood is filtered out. Okay. So you remember I talked about this in earlier in the course, right? People who do dialysis, because the blood cells are taken out of the body, they get destroyed, and so they become a little bit anemic. So you need to give them a bit of EPO as well. The other kind of dialysis is peritoneal dialysis, where dialysis fluid is pumped into the abdominal cavity, and then it drains back out into a bag. So these people are more mobile. They carry a bag with them to collect the urine, and then they have to empty it. Okay, both have pros and cons. Okay, and all you have to know is there are two types: hemodialysis, taking the blood out; peritoneal dialysis, you pump the fluid in. This is diabetes mellitus. Right? That's the diabetes that people are more familiar with. Okay, so there is a type 1 and type 2, which we'll talk more about later on. But in this case, if the body is not absorbing the blood sugar stays in the blood rather than into the cell, and it saturates the glucose transporter in the proximal tubule, right? I told you already. And if it's saturated, then you cannot absorb the excess glucose from the blood. And it stays in the filtrate, and then you end up peeing it out. So the excess sugar is gonna basically add more black dots to the filtrate now, and it sucks the water from the surrounding tissue, and it increases the urine production. Okay. So individuals with diabetes void large volumes of urine, which explain why they are often thirsty. But with medication, with the insulin, if it's type 1, then the insulin is going to help. If it's type 2, Then there are other medications that will help reduce the sugar level in the blood. Metformin is a common one that people might have heard of. Okay, we'll talk more about this in the endocrine unit. Last slide. Nephritis. Itis is inflammation. This is the inflammation of the nephron. And it's not a single thing. Nephritis can be as a result of other complications that are happening in the body. But in this case, when the nephron is inflamed, the glomerulus becomes even more leaky. Okay, more leaky. And when it's more leaky, then things that are not supposed to get filtered out starts to get filtered out. So protein is going to show up in the urine. That tends to make the urine very foamy. Blood cells might show up. White cells might show up. Right? So all these things are not good. So one type of nephritis affects the glomerulus, and it's because sometimes you might have an infection, basically. And the microbes, the bacteria is producing toxins that destroys these glomerulus, and it makes it more permeable. I don't think there's a lot of questions. I already told you this already. Okay, like there is proteins and large molecules, and the thing is, once they go into the filtrate, there's no way to absorb them back. Right? Protein is not even supposed to be in the filtrate to begin with, so you don't even have a transporter to take them back. And again, it goes back to the same theme. It increases the black dots in the urine, and then it just sucks the water from the surrounding, and you end up peeing more. Basically, anytime you pee more frequently and more volume than you normally would, it's a cause for concern, right? Like unless you're like drinking more water than normal, then sure, that's understandable. But if all else the same, and then you're peeing more frequently and more so than you normally would, then that's could be an indication that something it's not quite right. Okay, I don't think there's a lot of questions on these kind of diseases in quiz 3. Most of it is just the anatomy and the physiology aspect of it. Okay, that's it. No class on Monday. Just focus on doing the test number 2, and also study for the quiz number 3. Right. Next week we will start on the skeletal system. Okay, musculoskeletal system. All right. Thank you. See you guys later. Have a good one.